All right, guys, welcome to week one introductory of Math Divulged. Our class today is going to be Algebra Tricks 1. If you're joining us for the first time, we are Math Divulged. We're a bunch of competitive math veterans who are neither in high school or in college that are wanting to just give you a free online series of classes targeted at any student of any age who's interested in learning mathematics. And today's topic, like I said earlier, is going to be Algebra Tricks 1. So we're just going to go over that real quick. So for a lot of us, algebra is the first higher math subject that we're introduced to in school. And in competitive math, algebra problems tend to rely on tricks, then manipulations that reduce the problem to an easily solvable form. This is not limited to a certain difficulty level. You can find these manipulations in AMC 10 all the way into Olympiads. Now let me just find a way to mute notifications if that's possible.
Could I say something real quick, Naveen?
Yeah.
All right, so before we start, I'm Dylan. We have another TA, his name is Brian Liu, and we'll be the TAs for this class. So if you guys have any questions during this meeting, just ask me or Brian Liu. You can PM us, and other than that, yeah.
All right, I'm gonna find a way to mute all notifications if possible. That'd be nice. Why do I keep seeing the same person enter the waiting room over and over again? All right, that's fine, whatever it is. So let's get started. So the first one we see is, normally we see the quadratic formula pretty often because that's just a very powerful tool to solve equations. If you don't know it, here it is. If you have a polynomial in the form of ax squared plus bx plus c, then the solution to this is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is very, very well known. You're probably taught it in class during Algebra 1. And if you want a good proof for this, this is going to be, you can find this basically anywhere, from AOPS to like Khan Academy even. But the general trick is you complete the square. If you don't know what completing the square is, we're not going to go over it right now, but I recommend that you search that up in the meantime. We're going to move to our basic substitutions and manipulations. So that's your introduction. So let's just say that we had this equation here. We had x to the fourth minus 3x squared plus 2 is equal to 0. And my screen is frozen, that's great. So my app is being a little bit buggy, but that's okay, you can work around that. So what is the thing that you want to do here? Well, we know how to solve quadratic equations, right? And those are in the form of ax squared plus bx plus c equals 0. But it's hearing a lot of background noise. Someone not muted? Some people are not muted apparently. Could mute all again.
Sweet.
Whoever is not muted, yeah, I'm pretty sure I.
Naveen, you're muted, sorry.
So this is a little bit more technically challenging than last time it was. So we're back. So we have our equation, x to the fourth minus 3x squared plus 2 equals 0. So how would we solve this? Well, like I said earlier, we know our quadratic equations, right? Ax squared plus bx plus c equals 0. We know how to solve those. Now, you look at this and you realize that your x to the fourth and 3x squared, you can change these x squared into y. You can change all of these x squared into y. Now, if you do that, you end up with this expression. You end up with y squared minus 3y plus 2 is equal to 0. And if you're confused, you just go from x squared to y, and from x to the fourth to y squared, because x squared is equal to x to the fourth.
Naveen, sorry to interrupt again, but I think there's a common complaint that the board is a bit dark. Do you know how to make it white, I guess?
There shouldn't be like any way to do that. I don't think there is.
Or just use like lighter colored marker, I guess.
Yeah, this is as bright as it gets, so I don't know what's going on with that.
Because just use like white instead of like dark red, I guess, or a thicker pen.
All right. How does this work out for y'all? Can you see this? Send your response to Dylan, since I cannot see.
All right, this seems like a lot better.
All right, that works then. So y squared minus 3y plus 2 equals 0. Now this, you can use quadratic formula. If you know how to factor, you can also do that, and you'll get that y equals 1 and y equals 2. And once you do this, the value of x, so you have to plug it back in and get that x is equal to plus or minus 1 and x is equal to plus or minus the square root of 2. Remember, you're finding y in this expression here. So you need to make sure that you find x by plugging it back into y equals x squared. So let's move on to a different problem. Don't worry about all of this. We'll get into that shortly. So now we have a more challenging one. We have x to the fourth minus x squared is x to the fourth minus x minus 2 to the fourth is equal to 16. How would you go about solving this? Well, again, it's a quartic, right? You have an x to the fourth, and we only know how to solve quadratics.
Naveen, can you make the marker white again? People don't like the red. Sorry.
Shh. All right, there you go. So x to the fourth minus x minus 2 to the fourth is equal to 16. How would you solve this? Well, one trick that we can do is called the midpoint rule. Well, midpoint rule, there's not an actual name for this, it's just what we call it. And we'll say that y, y is equal to x minus 1. That's what we're going to try to do. And what we can do here, let's change that to green, is, well, here's what happens if you don't substitute. Jesus. So this is not working out right now. I don't know why the things are acting up on me, but today is not a good day for technology. So this is what we get if we expanded this. There's no way we can solve this, okay? But with this, you can get some better stuff. Jeez. We can change our x to the fourth into y plus 1 to the fourth. And we can change our x minus 2 into y minus 1. And this should say 16. Now, if you expand this and simplify, you get something a lot nicer, which is 2y to the fourth plus 12y squared equals 14. Now, if you look back, that kind of looks like this. That kind of looks like your x to the fourth minus 3x squared plus 2, right? Let's look at what happens. We can change our y to the fourth into z equals y squared. Can you guys see the blue? Is the blue okay for y'all?
The blue is good.
All right, blue is good. So z equals y squared. Now we can do this. And this is where we just substitute back in. You say, instead of y fourth, we put z squared. So 2z squared. And instead of 12y squared, we say 12z. So we're going to move the 14 over. 2z squared plus 12z minus 14 equals 0. And z squared plus 6z minus 7 equals 0. Now if you go over here, we can use our quadratic formula. And this gives us the value of z is equal to 1 and negative 7.
Naveen,
Yeah?
it should be 2y to the fourth plus 12y squared equals 16, as pointed out by a student.
Oh, yep. Sorry. Do you mind if I change the problem to say 14? Because the result doesn't change too much, right?
Go ahead.
All right. There's a reason I'm doing 14, is to show something a little bit better. So over here, we have z is equal to 1, comma, negative 7, and y is equal to 1, comma, negative 1, right? Now remember, your z is going to equal y squared. And the thing about z is equal to y squared is that when you square root all this stuff, how are you going to square root negative 7? Negative 7 is one of your solutions, right? That doesn't work. So you cannot square root negative 7 because that becomes an imaginary number. So z is equal to 1. And we get that y is equal to 1 and negative 1. And plugging back into this, you get y is equal to x minus 1. And when we do that, we get that x is equal to 0 and 2, right? And if you plug this back in, you'll get a, how in the world? Yeah, something is not right with this problem. I don't know what happened. No, this should be 16. Yes, this should be 16. All right, so we actually, this is originally 16. All right, that's better. So when we simplify, it went to 14 here, and this should also be 16. And simplifying gives 14. Whoever caught that 14, thank you so much for that. But let's check this real quick. 2 to the fourth minus 2 minus 2 to the fourth is equal to 16. Well, 16 minus 0 is 16, so that's pretty nice. So we know that 2 definitely works. 0 to the fourth minus negative 2 to the fourth. Well, that does not equal 16. Now this is a concept known as an extraneous solution. Now extraneous solutions arise when you're squaring or square rooting stuff, and square roots are always positive. But when you square root a number, you have to consider both positive and negative solutions. And this is equal to negative 16. So negative 16, our 0 is not a solution either. So we have a couple extraneous solutions. We have one where z equals to negative 7, and we have one where x is equal to 0. So our only solution is x equals 2. So whenever you square and square root stuff, keep in mind that these extraneous solutions may arise. So you have to check whether your solutions make sense. This is kind of the sanity check that we talked about in the very first lesson. Let's move to our next section, which is our next problem, which is if we have, okay, let's make this white since you guys don't like the red.
Naveen, by the way, when you have time, can you make Brian also a co-host?
All right, I can do that right now if you want.
Okay, cool.
You scroll down and find where he is in all these. Brian Liu, right? All right. Assign co-host.
So now if you guys have questions, feel free to message both Brian and me, because I am getting flooded.
All right. So x plus 1 over x is equal to 3. So what would be x squared plus 1 over x squared? Well, one way we can approach this is if we were to just find the value of x and then plug it in, right? Let's do that, and let's see what happens. And it's not going to be pretty. Let's multiply everything by x. So we get x squared plus 1 is equal to 3x. Now let's put this in our quadratic expression form, right? X squared minus 3x plus 1 is equal to 0. Using our quadratic formula, we get x is equal to 3 plus square root of 5 over 2. Look at our what we want to solve. At some point, we have to get x cubed plus 1 over x cubed, right? This is nasty. There is no way that you can solve it by just finding x and then plugging it in. It's not going to happen. So there's got to be a better way, right? Well, there is. There is a better way. What you can do is you can square the original expression. So let's do that. X plus 1 over x squared. Now if we expand this, we get x squared plus 2 plus 1 over x squared is equal to 9. Now look at this. And look at this. For some reason, that does not want to highlight right. So x squared and 2x squared show up. X squared and 1 over x squared both show up, right? And that's what we want to solve. So now we know that x squared plus 1 over x squared is equal to 9 minus 2, which is equal to 7. So there's your answer for that question. Now let's move on to a more challenging one. What about x cubed plus 1 over x cubed? Let's erase this. We need more space for this one. Well, let's just cube it and see what happens. X plus 1 over x, x plus 1 over x, and x plus 1 over x. This, if we expand it all the way, we get this again. And expanding, we get x cubed plus x plus 2x plus 2 over x plus 1 over x plus 1 over x cubed. And this simplifies down to x cubed plus 3x plus 3 over x plus 1 over x cubed. Now look again. We have our green terms. We have our x cubed plus 1 over x cubed. And now if you look again, we can factor a 3 out of this section over here. And that is just going to be our original x plus 1 over x, right? So this will become our green term, which is x cubed plus 1 over x cubed, plus 3, sorry, that will change to white, plus 3 x plus 1 over x. And we said that this was going to be this our original expression cubed, right? So this is equal to 27, because that's 3 cubed. This equals 27. This over here is equal to 3. So our green plus 3 times 3 is equal to 27. So therefore, x cubed plus 1 over x cubed is equal to 27 minus 9, which is equal to 18. Not too bad. So that's a more complicated one that you can do. After a lot of practice, you'll be able to do this pretty instantly. Like, it shouldn't take you more than 15 seconds once you get used to this a lot. So you can see how pretty powerful it is. Next thing we're going to talk about,
Naveen?
yeah?
So for the previous problem, the one where it was x to the fourth plus x minus 2 to the fourth equals 16.
Yeah.
I think on the board, it was accidentally written as x to the fourth minus x minus 2 to the power of 4 equals 16. So I think that's
right.
What 16 versus 14 all like came from.
Oh, I see.
Yeah, so it should be right on the handout. I think we can maybe say that.
Yeah. The corrected question should definitely be on the handout. Like, by the time the handout comes out, it will have the correct form of this problem. So don't dread too much about this. I just wanted to show you what extraneous solutions were, and 2, how you can reduce problems to get them down to problems that you already know, which is the entire point of algebraic manipulations, right? Let's move on to this one. And this is an old thing that we wanted to do, and we're just going to get rid of it because it's too complicated for this round. And our screen froze again. I think it's just an issue with the app. So let's talk about this equation. How do you evaluate the square root of 3 plus 2 times the square root of 2? Well, one of the powerful tricks of math is wishful thinking. What if we can break this up into 2 radicals that didn't have radicals inside of them? And let's say that we added them and it just happened to result in this. That's what wishful thinking is. And you can see that's exactly what's going to happen. Now, if you're wondering how we know that's going to happen, like how to guide your mind into wishful thinking, it's practice. Through practice, you develop intuition. And through intuition and practice, you'll actually see some similar problems that will teach you that this is how you solve these problems. So, first of all, there's this big, ugly square root in front of everything. And so let's just get rid of that, right? This square root is not good. So let's square the entire expression. We get 3 plus 2 root 2 is equal to, now what happens if you square this? If you square root x plus root y squared? Well, what you're going to get is x plus y plus 2 root xy. This kind of looks like what we have on the left-hand side of the equation, right? We notice that x plus y is obviously not going to be, it's not going to be a radical, right? So let's just say that x plus y, these are different colors, let's use yellow because it's bright. X plus y is equal to 3. And 2 root xy is equal to 2 root 2. So that means our xy is going to equal 2. So now we have x plus y equals 3, xy equals 2. What can we do here? Well, this is going to be another algebraic manipulation. We can change y into 3 minus x. And we can take our xy equals 2 and plug our value for y, plug our expression for y into that. So we get x, 3 minus x is equal to 2. We can rewrite this by expanding and rearranging as x squared plus 3x minus 3x plus 2 is equal to 0. If you use quadratic formula on this, or if you factor this, you'll get x is equal to 1 or 2. Now, which one is x? It's both, actually. We're looking for x and y, right? Notice that you can basically flip x and y and get the same result. So x equals 1, y equals 2, or x equals 2, y equals 1. It doesn't really affect what the final answer is, right? So we can say that our final answer is that this is equal to square root 1 plus the square root of 2, which simplifies to 1 plus square root of 2. And that is how you simplify with some algebraic manipulation and some squaring. So there is a formula to find out exactly when you can do this, but it's beyond the scope of this lesson. Like, I don't think I've ever used it. Dylan says he's never used it. So I don't think you'll ever need to know that. Let's look at this problem. It looks pretty intimidating at first, right? What is the value of square root 12 minus square root 12 minus square root 12 minus square root 12, and so on and so forth? So one of the most powerful things you can do is name something, right? We all got a name, and let's name this one. Let's call it x. And like you said, you don't like white either, do you? All right. So this is x now, right? Now let's look at our original expression. You notice that like there's a pattern that develops. You have square root 12 minus square root 2 minus square root 12. Whenever you see these kind of repeating patterns, there's probably some manipulation. That should be the clue to let you know I can probably substitute something to make the expression nicer. Now, what's the difference between this entire thing and this entire thing? Well, they're the same thing, right? This is also x. So we can actually change this into square root 12 minus x is equal to x. Now we use our problem-solving tricks. We square the entire expression. So this squared and this squared. And this will become, let's do a different color, 12 minus x is equal to x squared. If we rearrange, x squared plus x minus 12 is equal to 0. And if we use quadratic formula or factoring, we get x equals to 3 and x is equal to negative 4. But remember what I said earlier about extraneous solutions? We have to check if this actually makes sense. And 3, yeah, it makes sense. I can see the answer being 3. But negative 4, on the other hand, the square root of a positive number is always a positive number. I know people say that like you can square root negative, you can do this, it's equal to 4. I know that, but the square root of 4 is equal to 2. The square root is a function, and the function only has one answer. So if we square root this entire thing, this seems like a positive number, right? That square root should result in a positive value for x. Therefore, negative 4 is an extraneous solution. So this is wrong. So the answer is x equals 3. All right, let's go to logarithms. This is a pretty colorful page, as you can tell, but we'll get through those. So, how many people, okay, actually, let's not do that. That's going to overwhelm the chat. But if you don't know what logarithms are, let's put it this way. You should know by this point that 2 to the power of 3 is equal to 8. So what a logarithm says is, how many times do you need to multiply a number to get to a different number? So in the case of log 2 of 8, it's asking, how many times do you multiply 2 to get to 8? Well, 8 is equal to 2 times 2 times 2, and there's 3 2's in that expression. So our log base 2 of 8 is equal to 3. So let's just go over some properties of logarithms with some examples. So our first one says that c log ab is equal to log a of b to the c. Let's see an example of this to make it a little bit more clear, because notation is very hard to understand when you first see it. So our log base 2 of 8 cubed. So how many 2's does it take to multiply to get to 8 cubed? What we can do, we can bring that 3, this 3, we can bring that 3 down to the front of it to say that this is equal to 3 times the log base 2 of 8. Now, what is log base 2 of 8? Well, it takes 3 2's to get to 8. So the answer is 3 times 3 is 9. So it takes 9 2's. So 2 times 2 times 2 times 2, all those 2's, there's 9 of them. And that's going to multiply to 8 cubed. So the answer is 9. Next property is log base a of b plus log base a of c is equal to log base a of bc. Okay, but what does this mean? Again, example problems help you understand things. Log base 2 of 8 plus log base 2 of 4, what does that equal? Well, we know the log base 2 of 8 is 3, and the log base 2 of 2 is 2. Log base 2 of 4 is 2, right? So that's 3 plus 2 equals 5. And the answer is that log base 2 of 32 is equal to 5, because you multiply 2 5 times, and it becomes 32. What our property says is that instead of, finding each individual log, adding them, and then exponentiating everything, we can just say, hey, we have the same base. We can multiply 8 and 4 to give 32. So log base 2 of 32 is equal to 5. Next property is kind of the same thing. Instead of adding 2 logs with the same base, we're going to subtract them. The same way, instead of multiplying them, we're going to divide them. So let's take our previous example. Log base 2 of 32 minus log base 2 of 4. This one should be pretty straightforward. We just did 32 divided by 4 is equal to 8. Now, something I want you to notice with the blue and yellow properties is this only works if you have the same base. That base is this tiny number right here, right next to the log. This thing right here. That's the base. Remember, look at this. Log A, log A, log A, log A. You have to have the same base. This does not work if you have different bases. So you cannot do log base 2 of 4 plus log base 3 of 8. You cannot do that with these methods. Next property does involve something with different bases. That's if you have log base a of b times log base b of c is going to equal log a of c. Now, log base 2 of, let's look at an example to show what this means. What if you want to find base 2 of 8 times log base 8 of 64? What would that equal? Well, if you look at this, over here we have an 8, over here we have an 8. What our green property says is that we can basically drop these out to get log base 2 of 64. And if you count how many 2's it takes to get to 64, the answer is 6. 2 times 2 times 2 times 2 times 2 times 2 is equal to 64. So that's equal to 6. And that's what our property says. The last one that we're going to learn, it's pretty straightforward. Log base a of b is equal to 1 over log base b of a. So if the question is, what is the log base 4 of 2, using our, I don't even know what color that is. Is it pink? Is it purple? Doesn't really matter. Is equal to 1 over log base 2 of 4. And log base 2 of 4 is equal to 2, because 2 times 2 is 4. So that's going to equal 1 over 2. Memorize these. You have to know these. It takes some time to get used to the idea of how logs work, but hopefully these examples will teach you, give you some intuition as to how they work. Let's look at an example, right? Let's not spoil anything. I'm hearing, is audio still going?
Audio is fine.
Okay, yeah. I just heard the background noise cut out for a minute. All right.
Oh,
So our,
change it to not dark red. People can't see it again.
yeah, I prepared these in dark red, so I'll change it now. So let's look at this problem. It looks kind of intimidating, right? What is 1 over log base 2 of a plus 1 over log base 3 of a plus 1 over log base 4 of a, and then equals 1? So what is a? Well, you notice a lot of 1 overs, right? Let's scroll back to our previous screen. Log base a of b is equal to 1 over log base b of a. And log base 4 of, so we know that property, right? We can apply it here. Log base 2, 1 over log base 2 of a is log a of 2, right? This should make sense to you, right? It's just our purple property from earlier. And then we do the same thing for the other ones. Log a of 3 plus log a of 4 is equal to 1. So now you can add all these up, right? Log base, so remember this property, our blue property, where we can multiply the ones with similar bases, and if you're adding them together. So this should equal log a of 2 times 3 times 4 is equal to 1. Now we can simplify this. Log base a of 24 is equal to 1. Now this is just basically saying what a equals 1, a to the 1 equals 24. What is a? Straightforward. A is just 24, right? Easy one right there. Once you actually find the initial trick, everything simplifies really nicely. One thing I do want to talk about though is there's a special logarithm known as the natural log. Natural log, you don't really see many uses of it like before calculus really, but it's important to know regardless. Now the natural log is basically saying what power of e. Now if you don't know what e is roughly equal to 2.718. And e is a very useful number when it comes to things like compound interest, when it comes to things like summing up a lot of series, and even when it comes to trig later on and complex numbers. It's a very useful number, probably more useful than pi, not gonna lie. But the logarithm in base e comes up so much that we give it a name. We call it the natural log, and we denote it as ln of x, or ln of a in this case. So the last thing I want to talk about before we go to some problems is our ceiling and floor functions. This is still on, right? Are we recording? All right, we are. So floor function, let's say we had number 5.5. And this is in red because that's how I prepared it again, so I'm going to change it to white. Nice paint. Okay. So what is the floor of 5.5? What floor means is that we take only the integer part. So the largest integer smaller than x. Now, typically, you'll see it with any one of these two symbols, like, an actual floor. Whoops, an actual floor here. You can kind of see the floor part being highlighted. Sometimes you see this. I don't like this that much because it's not a good visual representation, but you see this quite often. But I would use this one because it's very clear what you're talking about. So what is the largest integer smaller than or equal to 5.5. Now, we know this is just going to be a 5, right? That's the largest integer smaller than 5.5. What about the floor of 5? Smaller than or equal to. Largest integer smaller than or equal to. And 5 still works for this. What about 4.99? This is 4. You should understand how that works by now, right? Now, what about the ceiling function? The ceiling is kind of the opposite. What is the smallest integer larger than x? And you notice this symbol right here? Like I said, you can kind of see the ceiling of the building being highlighted. So it's a good visual representation. I don't think there's any other ways to represent it because your generic one is taken by the floor. So let's do some examples to show exactly how ceiling works. What is the ceiling of 3.7? Ceiling of 3.7 is just 4. Oops, this should not say ceiling of x equals 3.7. This should say ceiling of 3.7. And we know that x equals 4. What about the ceiling of 2? Well, smallest integer greater than or equal to again. And the weight, and here's the thing, this is also equal to 2. It's not going to equal to 3. Even though it says greater than, it's greater than or equal to, so don't lose that. Now, what does this mean? Let's just say, for example, that we had floor of x is equal to ceiling of x. Well, floor is smallest integer less than or equal to. Ceiling is smallest integer greater than or equal to. The only way that this works is if the floor is actually, if both of these are actually equal to x, which means x has to be an integer. So this is only true if x is an integer. Something decently important there. Now, one of the tricky parts is when some people are doing floors of negative 2.5 or something, they just drop a decimal point and say that this is equal to negative 2. Nope, it's equal to negative 3. Negative 2 is not less than negative 2.5. This should equal to negative 3. Because you're trying to go below negative 2.5. And the same thing happens with ceiling. They see a negative 0.5 and their mind just autopilots and they say negative 1. Wrong again. This is 0. I think this is probably the most common silly mistake concerning floors and ceilings. With negative numbers, you tend to do this. So don't do it. This has been your warning. So if we have a name for the smallest integer that's less than or equal to, greatest integer less than or equal to, and smallest integer greater than or equal to, do we have a name for the fractional part of a number? Why, yes, we do. Let's get rid of all this. We do have a symbol for that, and it's typically denoted by curly braces. What color should we use for this? Let's use a light blue. We'll say this. And the more formal definition is that this is equal to x minus the floor of x. What does this mean? So 3.7, right? Is equal to x minus floor of x. Let's change this to white to make it consistent. So that means, you should know this pretty easily, right? This changes to 3.7 minus 3, and our fractional part comes out, which is 0.7. Fractional part's pretty easy to understand. Again, the silly mistake tends to arise with negative numbers, where we have, let's say the fractional part of negative 3.7 this time. That's not a nice brace. Hold on. There we go. Is equal to, and now some people, they just autopilot and say it's 0.7. Not exactly. This is equal to negative 3.7. And what's the floor? The floor is negative 4, right? So this is equal to negative 4. Fractional part is always going to be either between 0 and 1. It could be 0, it can't be 1. So this is going to equal 0.3. Let's make this light blue again. So that's floor and ceiling. So we still have some couple minutes to go through this. Dylan, do you want to say anything before we move on to problems?
Oh, I think we're good, Brian.
Brian, hello?
Yeah, we're good.
All right, we're good? All right, let's move on to some problems. So our first problem, evaluate, okay, that's not the right one. Log 2 of 3, log 3 of 4, log 4 of 5, dot, 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 log 2047 of 2048. This is, I'll give you about a minute to work it out. It shouldn't take like too long, but it requires some thinking. So I'll give you a minute. Okay, don't type the answers in chat. Just hold on to it for now, and yeah. All right, I think that is a minute. That minute has passed, and I did see a lot of the correct answer. So right before I said not to. Okay, yeah, the answer is 11. And how do you get 11? Pretty straightforward. If you go back to our log properties slide, we're going to make good use of our green property this time. And our green property says that log base A of B times log base B of C is equal to log base A of C. And this, we just keep doing it, right? Because look at this. All of this is going to cancel out. The 3's cancel, and then the 4's cancel, and so on and so forth, until all you're left with is log base 2 of 2048. Now, if you guys don't know your powers of 2, I recommend that you know them to at least to the power of 15. It's very, very useful. And if you know those powers of 2, you'll recognize that 2048 is 2 to the 11. So the answer is 11. Pretty easy start to this one. Let's move on to the next one. Determine the following fraction. 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2 plus dot, dot, dot. Now let's go back to one of our slides. Remember this problem? We're going to use the same trick of looking at the pattern and substituting x into the pattern. So let's say that this right here is x, right? So 1 over 1, oh, I actually, hold on, yeah. 1 over 1 plus 2 plus x is equal to x. Now we can add the bottom side of the expression, and then we will get a 1 over x plus 3 over 2 plus x is equal to x. And then we get 2 plus x over x plus 3 is equal to x. Now we can cross multiply, or if you want to just multiply everything by x plus 3. Let me move this up so we get more space to work with. If you multiply by x plus 3, you will get, let's use a different color, 2 plus x is equal to x squared plus 3x. Quadratic formula time. Let's put it into our form first. X squared plus 2x minus 2 equals 0. X equal to -2 plus or minus the square root of b squared minus 4ac, which is 4 plus 8 all over 2. Simplifying this down, we get x is equal to -1 plus or minus the square root of 3. Now, if you remember our radical problem, our square root 12 on a square root 12 on a square root 12, not all solutions work. -1 minus square root 3 is negative, and our fraction is clearly not negative. So we have another extraneous solution. So we can eliminate that one. So x is equal to root 3 minus 1. And this value of it, I forget exactly what, but it's like a 0.7 to be not too important. Next one, you guys are going to do again for a minute by yourselves. So let's do it. What is the value of 7 root 7 root 7 root 7 root 7 root 7 root 7 and continuing equals what? Give y'all a minute. Hold on to your answer. And when I say time, type your answer in private chat. Well, I said hold on to chat, but Dylan, are you here?
Yeah, what's up?
Can you check Discord real quick?
Yeah.
All right, guys. Like I said earlier, hold on to your chat for a bit. All right, there we go. So yeah, answer is 7. Nice paint. And there's a lot of spam of nice paint. Jesus Christ. All from the same person. Yeah, answer is 7. And pretty simple as to what's going on there. This is not too bad. Same motif. Substitute this for x, right? Root 7x is equal to x. Square both sides. 7x equals x squared. Now, if you factor it out, you'll get x equals 0, x equals 7. extraneous solution with x equals 0. I think we have time for one more problem after this. So let's do one more. Y'all ready? And this one will give a little bit more time. Problems are not going away. All right. If ln of x, okay, that's red. You guys don't like red. Ln of x plus ln of y is equal to 2.9, and ln x ln y is equal to 1. What is the value of this expression, log base x of y plus log base y of x? You guys have a couple minutes. This will be the last problem for the day since we're approaching 4 o'clock. Okay, let's see what you guys got. Same guy, just spamming. Okay, guys, don't spam, please. That's, well, saying that's probably gonna make you spam more. All right, let's just solve it actually, because let's get kind of stuck. So we first we see ln of x, ln of y quite a bit, right? Let's get rid of that. Let's say that ln of x, okay, yeah, that's red. Ln of x is equal to a. Ln of y is equal to b. So a plus b is equal to 2.9. Pretty straightforward substitution. And ab equals 1. If you're confused, we just reworded the first two equations with our substitution. So that makes stuff a lot simpler for us, right? What about this log base x of y stuff? That looks kind of familiar though, doesn't it? To go back to our logs page, kind of looks like our green property again, where we change bases. Log base A of B times log base B of C. What does that mean for this problem? Log base x of y, we know that, we know our log base e stuff, right? Log base e of x, and then log base e of y, right? Now let's see what we do here. When we multiply them, we change bases, right? So let's multiply these. Well, this should be, sorry, this should not be log base e. This should be log base x of y. And this should be log base e of y. Now, what does this mean? Let's change everything back to natural logs, right? Natural log of x times log base x of y is equal to natural log of y. So log base x of y is equal to natural log y over natural log x. That kind of makes sense, doesn't it? So that's another neat trick. It's just a rewording of our old green trick. So we can rephrase this. Instead of saying what's log base x of y plus log base y of x, we can say what's ln of y over ln of x plus ln of x over ln of y. And with a substitution, we can say this is equal to what is b over a plus a over b. Let's add these together. If we fully add these, we get a squared plus b squared over ab. Now you guys remember when we did this problem, let's pull it up. When we had x plus 1 over x is equal to 3, we found x squared plus 1 over x squared through squaring our initial thing, right? Through our initial x plus 1 over x. Let's do that here. What's a plus b squared? Well, a plus b squared is equal to a squared plus 2ab plus b squared. This should equal 8.41. If you guys don't know your squares, know them until 50 and know your cubes until 20 or 15. Actually, it doesn't really matter too much what you know your cubes to. But we can simplify this now. This is equal to our desired expression, a squared plus b squared, plus 2 times ab. We know what ab is. It's equal to 2. So our a squared plus b squared is equal to 8.41 minus 2 is equal to 6.41, right? Oops, the dot is not showing up right. There you go. And our AB, we know what AB is. It's 1. So what's our answer? Our answer for remember our initial question was, what's log base x of y plus log base y of x? That looks complicated. We simplified it down, and now we know our answer. Answer is 6.41. There you go. That's how you solve this problem. This question appeared on Texas A&M, the Texas A&M math exam. If you guys live in the Texas area, be sure to go to that contest because there's a lot of good questions. We talked about this in our first class, but one of the for fun things they do is called the Buzz Contest. Buzz Contest is where you just list properties and numbers. It's very intense, very fun. I recommend that you go. I'm pretty sure it's free. Is it free? Dylan, Brian, do you know if it's free or not?
The A&M contest?
Yeah.
I'm not sure.
I know as at least part of Quill Valley and Dulles, we never had to pay for the contest. So that's okay. So go to that contest. There's a lot of good problems. Their tests are based off of what subject in school you're in, and they focus on the questions from there. And that's where that problem is from. It is 4:05 right now, so we're probably going to end the meeting. If Dylan or Brian want to say anything, say things right now.
Yeah, and like it's been a while since I went to the A&M contest. I think I only went once, but if certain contests are not free, or if your schools don't provide access to it or anything like that, like be sure to like push your school to let you pursue your passions. I know like a lot of schools are like underfunded, underserved, and you'll be doing something great for your whole school. And for me, and like our school didn't offer math counts until, or our district didn't offer math counts until 7th grade. So, yeah, just like push for it. Yeah.
Oh, I guess there wasn't a proper dismissal. Yeah, so thanks for coming, guys.
Yeah.